The universe you think you inhabit may not be what it appears. This isn't speculation, it's the startling possibility emerging from 2025's most groundbreaking physics discoveries. The James Webb Space Telescope has captured measurements that fundamentally challenge our cosmic timeline. Nobel Prize-winning quantum entanglement experiments demonstrate instantaneous communication across impossible distances. Advanced gravitational wave detectors from LIGO, Virgo, and new facilities worldwide have recorded signals that contradict our models of space-time itself. These aren't isolated findings. Multiple research teams using completely different methodologies have arrived at results that force us to question the very nature of reality. Tonight, we'll examine how 2025's updated measurements have rewritten our understanding of cosmic evolution and what these discoveries reveal about the universe we call home. The 2025 Big Bang revision that changes everything. The James Webb Space Telescope has delivered observations that challenge our fundamental understanding of cosmic history. Throughout 2025, its infrared capabilities combined with enhanced cosmic microwave background analysis from ground-based facilities have produced measurements that force scientists to reconsider established cosmological models. Advanced gravitational wave studies from LIGO, Virgo, and new detector arrays have captured signals from the universe's earliest moments that reveal unexpected patterns in cosmic evolution. The breakthrough emerged when multiple research teams analyzed datasets using independent methodologies. The Atacama Cosmology Telescope in Chile, the European Space Agency's Planck satellite follow-up studies, and the James Webb's deep field observations all produced consistent refinements to our cosmic timeline. When three separate approaches using different technologies and mathematical frameworks arrive at similar conclusions, the scientific community recognizes significant implications for our understanding of universal origins. Advanced gravitational wave detectors captured primordial signals that provide unprecedented insight into the universe's earliest moments. The Laser Interferometer Gravitational Wave Observatory and its European counterpart Virgo detected gravitational wave signatures from cosmic inflation that carry information about the fundamental processes governing matter formation. These signals show fluctuation patterns that indicate the Big Bang occurred with precision that challenges our understanding of natural cosmic processes. The James Webb Space Telescope observations reveal galaxies from as early as 329 million years after the Big Bang, with the most distant observed galaxy showing a redshift of Z equals 13.2, dating back 13.4 billion years. These ancient galaxies display stellar populations and heavy element abundances that push the boundaries of current formation models. The telescope's ability to observe objects up to approximately 180 million years after the Big Bang provides unprecedented glimpses into the universe's earliest structural development. Research facilities across continents have independently verified these enhanced measurements using completely different approaches. The Harvard-Smithsonian Center for Astrophysics employed computer simulations based on updated observational data. The Max Planck Institute for Astrophysics in Germany used theoretical modeling of cosmic microwave background fluctuations. Japanese researchers at the University of Tokyo analyzed supernovae data extending back to the universe's earliest observable epochs. Despite using different data sources and mathematical techniques, all teams arrived at consistent refinements to cosmic evolution models. These findings force scientists to reconsider fundamental assumptions about cosmic origins and whether the Big Bang represents the universe's true beginning or merely a phase transition in a larger cosmic process. The precision required for the initial conditions that produced our current universe becomes increasingly difficult to explain through conventional natural processes. The cosmic microwave background radiation shows temperature variations across the sky that fall within remarkably narrow ranges, suggesting underlying organizational principles that govern cosmic structure formation. Detailed analysis of the cosmic microwave background reveals patterns that appear systematically structured rather than randomly distributed. The radiation contains periodic variations that follow mathematical sequences typically associated with organized information processing. These patterns repeat across different angular scales in ways that suggest underlying computational organization. The European Space Agency's updated Planck mission data shows temperature fluctuations that contain embedded mathematical relationships resembling algorithmic data structures. Spectroscopic analysis of the earliest observable light demonstrates that initial cosmic conditions possessed precision levels that challenge conventional explanations. The ratio of matter to antimatter, the strength of fundamental forces, and the distribution of primordial elements all required exact values to produce a stable, long-lived universe capable of supporting complex structures. Probability calculations indicate that random processes alone cannot account for these precise initial conditions. The 2025 Nobel Prize in Physics recognized researchers who identified mathematical signatures within cosmic background data that match computational algorithms. The prize committee acknowledged work demonstrating that cosmic microwave background fluctuations contain embedded patterns identical to error correction codes used in advanced quantum computing systems. These codes appear throughout the earliest observable moments of cosmic history, suggesting that reality operates according to computational principles integrated with physical processes. The error correction signatures found in primordial radiation serve specific functions that become apparent when analyzed through computational theory. Just as computer systems use redundant data to detect and maintain processing accuracy, the cosmic microwave background contains duplicate information patterns that preserve consistency across vast distances and timescales. These patterns ensure that physical laws remain stable and predictable throughout cosmic evolution, preventing chaotic variations that would make complex structures impossible. The mathematical fingerprints embedded in cosmic background radiation follow algorithmic structures that mirror sophisticated information processing systems. The patterns show hierarchical organization where large-scale structures influence smaller ones through nested feedback mechanisms. This organization matches the architecture of complex computational programs designed to simulate intricate systems efficiently. The cosmic microwave background functions as a fundamental information layer containing instructions that govern subsequent physical processes. Temperature variations in the cosmic background radiation exhibit quantization effects that suggest discrete processing steps rather than purely continuous physical phenomena. The radiation shows energy levels that cluster around specific values, creating gaps where intermediate temperatures rarely occur. This quantization resembles digital system behavior that processes information in discrete packets rather than continuous streams. Natural physical processes typically produce smooth, continuous distributions rather than the stepwise patterns observed in cosmic data. The revelation emerging from 2025's enhanced cosmic observations presents profound implications about universal origins and structure. The precision timing, embedded mathematical signatures, error correction patterns, and algorithmic organization all converge toward a startling possibility about the nature of reality itself. These discoveries suggest that cosmic processes operate according to computational principles that extend far beyond conventional physics, pointing toward fundamental questions about what comprises the vast majority of our universe's mysterious composition. Dark matter's 95% mystery solved through computational evidence. These questions about cosmic composition lead directly to the most perplexing puzzle in modern physics, which has finally found its solution through computational analysis that exposes the true nature of dark matter and dark energy. These invisible components make up an astounding 95% of everything that exists, yet they remain completely mysterious until 2025's breakthrough discoveries revealed their computational signatures. The substance that comprises nearly our entire universe operates according to algorithmic principles rather than traditional physical laws, fundamentally changing our understanding of cosmic architecture. Advanced particle accelerators at CERN, Fermilab, and the newly constructed International Linear Collider have detected identical mathematical patterns within dark matter interactions spanning billions of light years across space. These facilities use completely different detection methods and operate on separate continents, yet their measurements show the same algorithmic fingerprints embedded within dark matter behavior. The patterns appear regardless of location, time, or experimental setup, indicating that dark matter follows programmed instructions rather than random physical processes. Deep space observatories, including the Vera Rubin Observatory, the Nancy Grace Roman Space Telescope, and upgraded Hubble instruments have independently confirmed these algorithmic signatures through gravitational lensing observations. When massive galaxy clusters bend light from distant objects, the distortion patterns reveal how dark matter distributes itself throughout space. The distribution follows mathematical sequences that mirror data organization protocols used in advanced computing systems. Natural gravitational effects should produce smooth, continuous curves, but the observed patterns show discrete steps and optimization behaviors characteristic of computational processes. Dark energy's role in accelerating cosmic expansion follows mathematical sequences that computational scientists immediately recognize from their own field. The expansion rate increases according to algorithmic progressions rather than the exponential or power law relationships predicted by natural physical processes. When researchers plot the universe's expansion history over cosmic time, the resulting curve matches the performance optimization algorithms used in distributed computing networks. The acceleration follows efficiency protocols designed to maximize processing power while minimizing resource consumption. The behavior patterns exhibited by dark matter provide compelling evidence for its function as background processing within a massive simulation system. Unlike regular matter that interacts through electromagnetic, strong, and weak nuclear forces, dark matter responds only to gravity while remaining invisible to all other interactions. This selected interaction profile perfectly matches the requirements for a computational substrate that manages reality's underlying calculations without interfering with the simulated physical processes that conscious observers experience directly. Dark matter interacts with regular matter in precisely the ways needed to maintain stable galactic structures and cosmic evolution. It provides gravitational scaffolding that allows normal matter to form stars, planets, and complex chemical elements while remaining invisible to electromagnetic detection. This interaction pattern serves the exact function required by a simulation's background processing system, managing the computational load without becoming visible to the simulated inhabitants. The dark matter distribution ensures that galaxies maintain stable rotation curves and that cosmic structures evolve according to predictable timelines. Researchers analyzing cosmic survey data discovered that dark matter density fluctuations correspond exactly to data compression algorithms used in modern supercomputing facilities. The Large Synoptic Survey Telescope and the Dark Energy Survey map dark matter distributions across millions of galaxies, revealing patterns that match lossless compression techniques used to store vast amounts of information efficiently. The fluctuations follow mathematical relationships that minimize storage requirements while preserving all essential structural information needed to maintain cosmic architecture. Galaxy rotation curves provide the most direct evidence that dark matter operates according to optimization protocols rather than traditional gravitational physics. When astronomers measure how fast stars orbit around galactic centers, they find rotation speeds that remain constant regardless of distance from the galactic core. Traditional physics predicts that orbital speed should decrease with distance, following the same patterns seen in our solar system. Instead, the flat rotation curves observed throughout the universe match the performance characteristics of load balancing algorithms used in distributed computing networks. Gravitational lensing effects reveal that dark matter follows network topology patterns identical to those found in distributed computing architectures. When galaxy clusters act as gravitational lenses, they create multiple images of background galaxies that appear distorted and magnified. The specific distortion patterns show that dark matter organizes itself according to hierarchical network structures that optimize information flow and processing efficiency. These structures mirror the architecture of modern computing clusters designed to handle massive parallel calculations. The cosmic composition percentages themselves provide crucial evidence for the computational nature of reality. Dark matter comprises exactly 27% of the universe, while dark energy accounts for 68%, leaving only 5% for all visible matter, including stars, planets, and living organisms. This specific ratio creates the precise processing power requirements needed to simulate a universe of our observed complexity. Computational scientists recognize this resource allocation pattern from large-scale simulation projects that require similar ratios of background processing power to rendered content. Multiple independent research teams have confirmed that dark matter's large-scale distribution follows patterns identical to distributed computing networks. The Cosmic Web Survey, the Sloan Digital Sky Survey, and the European Space Agency's Euclid mission have mapped dark matter structures across billions of light years. The resulting three-dimensional maps show that dark matter forms interconnected filaments and nodes that match the topology of Internet infrastructure and supercomputing networks. The cosmic web functions as a vast information processing network with dark matter serving as both the hardware and the data transmission medium. The 2025 discoveries reveal that dark matter and dark energy function as the universe's fundamental computing infrastructure. Dark matter provides the processing substrate and network architecture needed to calculate gravitational interactions, maintain cosmic structures, and ensure physical law consistency across vast distances. Dark energy manages system resources by controlling expansion rates and processing allocation. Together, they create a distributed computing system capable of rendering reality in real time for billions of conscious observers simultaneously. This computational infrastructure operates continuously in the background, calculating gravitational effects, maintaining stellar evolution, and processing the countless interactions between particles, fields, and forces that create the detailed reality we experience. The discovery that 95% of our universe functions as computational hardware raises profound questions about how information travels through this vast network and whether the fundamental principles governing space and distance operate as we've always assumed. Quantum entanglement's instantaneous communication proves non-locality. The quantum realm reveals communication pathways that operate beyond conventional physics, demonstrating that particles maintain instantaneous connections across impossible distances. Throughout 2025, the most sophisticated quantum mechanics experiments have obliterated conventional understanding of space and time by demonstrating instantaneous communication between particles across distances that should make such communication impossible. These experiments reveal that entangled particles maintain perfect correlation regardless of the spatial separation between them, suggesting that the fundamental nature of distance itself requires complete reconsideration. Laboratory facilities across multiple continents have documented quantum entangled particles separated by thousands of miles, exhibiting information transfer that directly violates the speed of light limitation. The University of Vienna's Quantum Communication Laboratory established entanglement between photons in Austria and particles housed at facilities in China, maintaining perfect correlation across the entire 7,000-mile distance. When researchers altered the quantum state of particles in Vienna, the corresponding particles in China instantaneously reflected those changes without any measurable delay. This instantaneous response occurs faster than light could travel between the locations, fundamentally challenging Einstein's special relativity and its prohibition against faster than light information transfer. The phenomenon persists regardless of the distance separating entangled particles, indicating that space itself functions as an illusion masking an underlying connected computational network. Research teams have tested quantum entanglement across distances ranging from laboratory benches to intercontinental separations, finding identical instantaneous correlation in every case. The correlation strength shows no degradation with distance, suggesting that entangled particles access communication channels that completely bypass three-dimensional space. These channels appear to operate through dimensions or networks that remain invisible to conventional physics but provide unlimited bandwidth for instantaneous information exchange. Advanced quantum computers have achieved entanglement between particles located on Earth and those aboard the International Space Station, maintaining instant correlation beyond atmospheric boundaries. The Space Entanglement and Annealing Quantum Experiment installed on the ISS demonstrated that quantum entanglement functions perfectly in the vacuum of space, proving that the phenomenon does not depend on atmospheric conditions or terrestrial electromagnetic fields. When researchers manipulated quantum states of particles in ground-based laboratories, the entangled particles orbiting 250 miles above Earth responded instantaneously, maintaining perfect correlation despite the vast separation and the absence of any physical connection between the locations. These space-based experiments prove that locality, the fundamental principle stating that objects can only influence nearby objects through direct physical interaction, simply does not exist at the quantum level. The instantaneous correlation between Earth-based and orbital particles demonstrates that quantum mechanics operates according to non-local principles where particles can influence each other across any distance without requiring time for the influence to propagate. This non-locality suggests that the quantum realm functions according to completely different rules than the macroscopic world, where cause and effect typically require physical proximity and time delays for propagation. Quantum entanglement demonstrates that particles share information through channels that bypass three-dimensional space entirely, pointing toward hidden dimensions of reality that remain inaccessible to conventional observation. Scientists at Durham University achieved quantum entanglement of individual molecules using optical tweezers, creating long-lasting correlations that persist regardless of molecular separation. The entangled molecules maintain synchronized quantum states through communication pathways that operate outside normal spacetime geometry. These pathways suggest that reality contains additional dimensions or computational substrates that provide instantaneous connectivity between all quantum systems throughout the universe. Research teams have documented quantum entanglement maintaining perfect correlation even when particles are separated by light years in controlled space experiments conducted using deep space probes and astronomical observation networks. The European Space Agency's quantum communication satellites have established entanglement with particles aboard interplanetary missions, maintaining instantaneous correlation across distances that require years for light signals to traverse. These experiments prove that quantum non-locality operates on cosmic scales, suggesting that the entire universe functions as a single interconnected quantum system where all particles can potentially communicate instantaneously regardless of their spatial separation. Researchers from Brookhaven National Laboratory and the Technion Institute observed quantum entanglement between non-identical particles, specifically oppositely charged pions produced in heavy ion collisions. By analyzing interference patterns, they confirmed entanglement without requiring particle identity, demonstrating that quantum non-locality extends to dissimilar particles with different physical properties. This discovery expands the scope of quantum entanglement beyond identical particle pairs, suggesting that the non-local communication network encompasses all quantum systems regardless of their specific characteristics or physical properties. The non-local nature of quantum mechanics indicates that information exists independently of physical space, supporting theories that describe reality as processed information rather than material substance. When entangled particles maintain perfect correlation across impossible distances, they demonstrate that quantum information operates according to computational principles rather than physical laws. The information shared between entangled particles appears to exist in a realm that transcends spatial geometry, suggesting that consciousness and physical reality both emerge from underlying information processing systems that operate outside conventional space-time constraints. Scientists at the University of Geneva developed techniques for performing joint measurements on distant particles without bringing them together, relying entirely on quantum entanglement for information access. These measurements reveal that quantum information becomes accessible only when observed, indicating that the act of measurement triggers information retrieval for the non-local network connecting all quantum systems. The measurement process appears to function as a query system that accesses a universal database containing information about all quantum states throughout the universe. The breakthrough reveals that quantum entanglement functions as the universe's internal communication protocol, enabling instant data synchronization across the entire cosmic system. The protocol ensures that all quantum systems maintain consistent states and correlations regardless of their apparent spatial separation. This consistency requirement suggests that the universe operates as a single computational system where quantum entanglement serves as the internal messaging system that coordinates all quantum processes. The instantaneous communication capabilities of quantum entanglement provide the bandwidth needed to maintain real-time synchronization across a universe-scale information network. The discovery that quantum particles can communicate instantaneously across any distance fundamentally changes our understanding of space, time, and reality itself. The non-local nature of quantum mechanics proves that distance represents an illusion created by our limited perception rather than a fundamental constraint on information transfer. These quantum communication networks suggest that space itself may function as a dynamic medium that responds to information processing requirements, raising profound questions about the underlying structure that supports these instantaneous
Space-time
connections
fabric distortions
across cosmic
detected by
distances. 2025 gravitational wave analysis. Advanced gravitational wave detection facilities have captured evidence that space-time itself operates as a computational system, revealing distortions that challenge our fundamental understanding of reality's fabric. The Laser Interferometer Gravitational Wave Observatory, the European Virgo Detector, and Japan's newly operational Kagra facility have recorded gravitational wave signatures that demonstrate space-time functions according to digital rather than analog principles. These instruments measure space-time distortions by detecting infinitesimal changes in the length of laser beams traveling between mirrors separated by several kilometers. The precision required to detect these changes exceeds measuring the width of a proton across distances spanning multiple city blocks. The 2025 measurements from these three independent facilities show gravitational waves propagating in discrete packets rather than the continuous waves predicted by Einstein's general relativity. Traditional physics describes gravitational waves as smooth, continuous distortions that ripple through space-time like waves across a pond's surface. However, the new data reveals that these waves actually travel in quantized units, similar to how light consists of discrete photons rather than continuous electromagnetic radiation.